Hi everyone, welcome to this video on tree recursion and data abstraction. For those of you who are currently subscribed to me, this is part of a series of videos I'll be producing for Computer Science Mentors, which is a teaching part of UC Berkeley for the CS courses. This will be covering the introduction to programming, which is done in Python, and we'll be going through concepts like this for the next coming weeks. For those of you who are in my section, welcome back. I hope this review of what we did this past week will be helpful, and let's dive right in. So the first question is a recursive question. It's is sorted, which takes in an integer n and returns true if the digits of that number are increasing from right to left. So this is a number manipulation problem basically, and it's somewhat of a linear recursive problem rather than tree recursion. So we can start by looking at what we want to do for some potential base cases. We see that we have, if a number here is a single digit, we return true because there's no chance that it could be increasing or not. It will always be true. Here we have 2, 2, 2, 2, 2. This is true because the numbers are essentially increasing. It's equivalent. They're not decreasing is the important thing. This base case is an example of all true. The numbers are always increasing from right to left. And then in this last example is where it gets interesting. We see that we have 7, 8, 0, 9. So this 0 is what's causing this case to fail, and this is basically what we can base our false check off of in this recursive function. So to start, we want to figure out a way that we can grab the current digit that we're on, which would be here, and then separate it from the rest of the numbers. So if we have something like 9, 0, 8, 7, 6, 5, 4, 3, 2, 1, we want to grab this 1, and then we want to store the rest of the number to refer to later. So recall that to grab this rightmost digit, or the least significant digit, we can do something like number modulo 10. Likewise, how would we grab the rest of the number here, the more significant digits? We can do n floor division 10 to drop this least significant digit. So this will correspond to there, and this will correspond to the rest of the number. So using this, we can first assign variables. So we can have rightmost digit is equal to n modulo 10, n being passed in from here down to there. And then we'll have rest is equal to n floor division 10. There. So now that we have these variables set up, we can start creating our truthy case, our false case, and our recursive call. We know that we can follow this structure because this is a Boolean recursive problem. We either return true or false, or we have to perform some form of a recursive call to keep this going. So let's start with our truth case. We can have if, and now what do we want to do in this if case? Well, we want to see if there's anything left. If there's nothing left, then we're done. So we can do if rest equals 0, then we'll return true, because by this point the function should be true if we haven't found a decreasing number in the right to left sequence. So we'll do return true. Now what do we want to do for our elif case? This elif case will be the false case. So I'll do truthy case elif, and then we'll have this be our falsy case. Now here we want to do something that checks if something like 0 and 8 occurs, that we see that this 0 is not greater than 8, and then we want to return false. So how will we go about doing that? Well, we know that we have the rightmost digit defined here, and we have the rest defined here, and we can use a similar logic as we did on the rightmost digit to grab the second least significant digit. So let's try that. So we have rightmost digit greater than rest modulo 10. Now, what this does in the rest modulo 10 case is, say in the example 2, 3, 2, 1, our 1 is our RMD, and 2, 3, 2 is our rest. Now we'll take 2, 3, 2 and grab this as our new rightmost digit, so that we're left with that 2 here. Okay, so now that we've written our if and our elif cases, we can go to our else case. So here we'll write our else case, and this will just be a classic recursive case. So we know that we'll do return something involving our function, and we want to think, what do we want to do to this function? Well, the only way to progress through this function is to continuously drop the rightmost digit and take our more significant digits and keep passing it through the function to check if there's a false or not. Otherwise, it will run out and we will return true. So all we have to do here is write rest, and we're done. This is our isSorted function, and it's complete. All right, now moving on to a more complicated problem. This is tree recursion rather than standard recursion. So I'll give you a second to read this video. You can pause it, take as long as you want to read this and the doc test, and I'm just going to go straight right into solving this problem now. All right, so here we have this function Mario number, which takes in level, and it has this doc test as specified and a few example cases. And we've conveniently written the skeleton out for you so that you can see how complex this problem should be. Now, this question is a little tricky in the fact that the recursive case may not be immediately clear, nor maybe necessarily even the return for your base case and your alternate base case. So what I'm going to do is I'm going to write out the code, explain kind of the logic behind it, but the intuition to that logic will come with practice and building these diagrams. So I'm also going to draw the diagram after so that you can see actually why this works, because this logic or code alone may not make complete sense. All right, so let's dive into this problem. So we can assume from this doc test that we'll have some base case involving level. Anything left, just like the last problem. So what we want to write is we want to check if level is equal to 1, which is the smallest size that will possibly be. If level is equal to 1, that means we successfully traversed from the start being the 1 and the end to being 1, and we can return 1, because that's one way that Mario can traverse. Now, Mario cannot step on anything that's a 0, so we want to check if any rightmost digit is a 0 while we traverse. So if level modulo 10 is equal to 0, then this is not a valid way to traverse and will return a 0. Now we can move on to our recursive case where we'll return something, but this is where it gets a little confusing. In tree recursion, we're returning 2 or more recursive calls, and that's what makes it cause this tree structure. So we know that we have to write Mario number, and then we have to write it again, which I'll do for convenience down here with a plus. But what makes these two calls different? Well, in this first call, we want to just see if Mario travels from one digit to the next. In the second recursive call, we want to see if he hops from one digit to the one after it. Therefore, we're going to take level, floor divided by 10 for the first one, in similar logic as we did in the previous problem. And then this next one, we're going to do level, floor division 10. But then we'll take that and floor divide it again by 10, so that he hops, basically skipping. This code can also be written in a more clean way, equivalent to level floor divided by 100 to skip the 2 spaces. Also, I'd like to point out that the reason why we use a plus here instead of something that you might have seen before, like and or, is because and or ors are good for Boolean values, but if we're summing numbers or summing up the ways that we can do a problem, we want to use a plus so that we can actually sum the number of ways that Mario can traverse through something. That's why we use a plus there. So now that we actually have all of the code written out, I think it helps a lot to see a diagram as to why this is true. So we can walk our way through our code using this diagram to verify that it is indeed true, and this is a really great way to understand tree recursion. So this problem gives us 0, 1, 0, 1, 0, 1. So we can start with this as basically the root of our tree is what we call it, our starting point. Now we see that we have if level equals 1, return 1. This is not true because we have a full node. It's not just 1, so we're going to skip this line here. Now we can check elif level modulo 10 equals 0, return 0. Well, if we do level modulo 10, it ends in 1, so this is not true, and we don't return a 0 either. So now we walk into our recursive case. Our recursive case will just run the functions. So our Mario number level floor divided by 10 will give us this, while floor divided by 100 will give us this. We can walk through our logic again on the left branch. We see that this elif condition is now hit, where we have a 0 in the rightmost digit, and we return a 0. So I like to write return value of 0, and this branch is dead. Now, similarly, we can apply this logic again. We can go to our other branch and check our conditions and we see that we can't satisfy anything. So once again, we branch with our recursive call and we get 1, 0, and 1. 1, 0 will meet the same fate as the other branch and the return value will be 0 and end. While 1 does indeed meet level equals 1, therefore we will return 1. And now that we have a return value of 1, the sum of the ways we can do anything is equal to 1, and that's how this doc test of 1 comes to exist. So I think this diagram of a tree is actually super helpful for understanding tree recursion and summing, and we can see that these bad paths here have a return value of 0 and have a return value of 0. But this good path here has a return value of 1, and that's how we get our answer of 1. All right, now we're going to start the make change problem. I'll give you a bit of time. You can pause the video, read the doc test, read what the problem's about, and then I'm going to dive right into doing it. All right, so this make change problem is basically a reworded coin change problem, which is an infamous coding question, programming question, interview question, whatever. It's very prevalent. And this is basically modified so that we now have these 1 cent, 3 cent, and 4 cent coins. So this problem, you can use a bit of pattern matching and intuition to solve it, but this is a trickier problem to just naturally get, and it has a lot more recursive calls, so you have to trust in this recursive leap. So we can first, based off the doc test, use this major hint about 1 cent, 3 cent, and 4 cent coins. So in this case, we have this 0 case, and then followed by a bunch of skeleton code. So we can try to figure out first, in what case will we want to return 0? Well, there's no way to make change if n is less than 1, right? That's the first thing. If we have 0 cents, we're not going to get any change, so we can write if n is less than 1. Now, what possible ways are we going to start making change, though? Well, if n is 1, we're not going to make any change. But if n is 2 or lower, then there's going to be ways we can make change. So we can write n is less than 3, which is also equivalent. If you want to do n is less than or equal to 2, that's fine. For this problem, I'm using n is less than 1, 3, and then naturally n is less than 4, because that's basically what the doc test kind of hints you towards. So in this n less than 3, we can try to break down what this recursive call will be. So given that we're going to be summing the number of ways that we can make change, we're going to need to return a 1. If we don't return a 1, it's not going to actually keep track of the number of ways we can sum to make change. So now we'll have a 1 plus something about a recursive call that we're doing. We only have make change as a function, so we'll make a recursive call to that. And there's something we want to do about n though. If we have 2 coins and we want to make change for it, then that means that our only option is to have a 1 cent coin and a 1 cent coin. Therefore, if I ask for change for 2, you'll first give me back a 1, and then you'll give me back a second 1. So in our make change problem then, we'll subtract 1 from our n because you're giving me back 1 coin first, and that's our recursive call. In this specific scenario, you can also write return n, just because that is equivalent mathematically, but that does defeat the point of understanding recursion in this problem. And we'll make some helper variables to accomplish this. So we want to recall that we want the minimum number of coins, not all of the ways, not the largest, we want the minimum number. So we're going to have to do something involving minimum in our future return statements. So what goes into that minimum function though? We can't put that full 1 plus make change and minus 1 in there. So instead we'll make a helper variable. So we'll make something called by 1s and by 3s. And this refers to the 1 cent and 3 cent coins that are our option when we're using this n less than 4 case. So we have by 1s and by 3s are both equal to 1 plus make change. Make change. But there's going to be a difference in their actual n cases. So by 1 cent coins, we already proved will be n minus 1. Likewise, then we can assume that if we're using 3 cent coins, then we can put n minus 3. So then we have our by 1s and by 3s, and we want to see the minimum number of coins we can use to make change for that. So what this minimum will do is we'll actually compare the sum at the end of these trees. So let's say we have like a 3 here, and we walk down the tree, traverse 3 versus getting a 1 and a 1 and a 1. Then we'll see that this path is the shorter one and return that minimum value. So we'll put in by 1s and by 3s. Now, using complete identical logic, we can just make a larger version of this again as our final else case for recursion. So we'll have buy 1 cent coins, buy 3 cent coins, and buy 4 cent coins, which is the largest denomination now. Likewise, each one will have a 1 to sum up the amount of ways we can do this. We'll write make change again in all of them. And then the only thing that will actually differ is then what we're doing to n. So now we can write n minus 1, n minus 3, and correspondingly n minus 4. And then our minimum will be buy 1 cent coins, buy 3 cent coins, and buy 4 cent coins. And there you have it. That's the answer to this make change problem, which is also very similar to the infamous coin change problem. All right, so now I'm going to move on to abstract data types, which is essentially object-oriented programming in disguise. So for the sake of this class, CS61A, we're going to call them abstract data types, but this is starting to get having objects have attributes and modifying them. So I'll give you a moment again. You can pause the video and read through this if you want. Otherwise, I'm going to start walking through this. All right, so here we have elephant. Elephant can take in the name, an age, and if it can fly or not. And we basically construct an elephant, in this case Dumbo, with the name Dumbo, an age of 10, and Dumbo can indeed fly. So now we have these helper functions, though, that we want to fill out. Now, why do we even care about having these helper functions? We know in lists, we could just write elephant 0 if we want his name, right? Elephant 0 will refer for this 0 to the 0th index element, which is name. Likewise, we can write elephant 1 and get his age at the first index. So the reason why we want to use these helper functions, though, is let's say something changes about the elephant. Let's say we store it in a different data type, or we want to add more indices or something else. This allows us to have these helper functions, elephant name, age, and can fly, that we'll use throughout the rest of our code. And we don't care really about how we get the name, the age, or if he can fly. Rather, we only care that we know we will get the name, his age, or if he can fly. So these helper functions will basically then abstract away the actual logic of getting these things, and we can just trust in the helper functions in future parts of our code. For now, we know the structure of elephant, and we can return E0. And we know right now that this will return his name. Similarly then, for the rest of the question, we can return E of 1 for elephant age, and return E of 2 for elephant can fly. Now, if you're confused on how 0, 1, and 2 match up, just remember that in a list in Python, we can call this the 0th index, the first, and the second. And we can grab it by just using the square bracket notation at the end of the object passed in, because E is passed in here at the start of every function. All right, so moving on now to the next part of this worksheet. I'll give you a few moments to read this. Pause the video again if you feel like you need to. But this is basically a list comprehension, which is something unique to Python with the square bracket notation. So this function does return what we want, but there's something wrong about this implementation. Now, this may not be immediately obvious, because how can something be wrong if this is the correct result, right? Well, this problem actually violates the abstraction barrier. We're using elephant 0, which means we assume we know how an elephant's data type is structured. This is assuming that we know that elephant equals some form of a list where their name is here, followed by other things. But what if we change this data type in the future, as I mentioned before? Then we want to use that function we made, elephant name. And then we can take in this elephant in this list of elephants. So what this simple change does is we always know that elephant name will give us the name, as we said, right? So now if we change the code in the future, it will always work, while elephant 0 may not necessarily work in the future. All right, so now moving on in kind of reverse style logic, we can fill out the constructor for the given selectors. So we see that we have elephant name, elephant age, and elephant can fly. So what's going on here? This is kind of a different notation than we saw before, right? So now, like we saw in the previous problem, that elephant has this certain data structure here. We want to create a new version of that that matches what's found here. So how do we go about tackling that, right? Well, we can see that we're doing something with elephant first index, and then we're going deeper. So we have a list inside of a list, which is valid in Python. That's called a deep list. And then we have one extra index here, and then nothing else seems to come after this. So elephant 2 is gone now. So we can kind of visualize this in the form of, we have a list. This list inside has 2 elements, 0 and 1 go here. And then we have this here on a shallow level as another value here. So now given this structure, what can we do for this constructor? Well, we have name, age, can fly, and we can just fill it into this form here. So we can return, once again, a list, and this list will be of the shape with a deep list, name, age, and then on the shallow level, can fly. And we can double check this works because if we call this e of 0 will give us this output, a list of name and age. If we want to grab the name of it, we have to call e0 to step into this deep list, and then we'll actually get name. All right, and then moving on for question 4, then how can we write the fixed elephant roster function for the constructors and selectors in the previous question? Well, this is a bit of a trick question. As I mentioned before, the reason why we use these helper functions, and we've redefined them here, is so that we can avoid any abstraction barrier issues. So because we're using now elephant name, taking an elephant, we're blind to the fact that this underlying data type changed, hence why it's called an abstract data type. So this is actually a trick question. No change is necessary because we followed the proper abstraction rules. All right, so now we're on to the optional problem. This optional problem is a little weird. We see that we have name, age, and can fly, which match up to this example of Chris Martin, 38 and false. And then we have elephant name Chris, which passes this object into the function elephant name, and we get Chris Martin. Likewise, the rest of the doc tests imply that structure, but we see here that we have something different. Rather than e of 0, we're calling e on the string name, e on the string age, and then e on the string can fly. So these helper functions, name, age, and can fly, take in this elephant object here, but then use this elephant object again followed by a string. So this won't right now give us what we're looking for. Hence we have to fill in this select command here, which is a nested function in elephant. Hence this can reference elephant's name, age, and can fly parameters passed in. So this is a bit of a weird problem, and this is more of a challenge problem with helper functions and this concept of abstract data types and abstraction barriers. So what do we want to do first? Well, we see that select command gets this parameter command passed in through name, age, and can fly. Because if we say e on name, e on age, or e on can fly, this is actually going to step into this helper function. And this name string, for example, will then become command. So we'll write statements corresponding to each of the strings that we know we need to cover, which if command equals name, else if command is equal to age. Then we also have the last check, which is command is equal to can fly. And then we'll leave an else if this is just not possible at all, like this. So first we can fill out this else case. If none of these 3 commands are happening, then we can say that this is violating an abstraction barrier. You can write whatever message you want here, but basically what this means is that we know that elephant has a name, an age, and if it can fly, but we don't know anything about it yet. So if we don't know anything else about it yet, then we can't assume that something exists, thus it's violating the abstraction barrier. Now, in the case that we do have a name, age, and can fly, then we can just write return for all of them. And then we can think about what are we actually returning. Well, this problem is actually simpler than it looks. Select is a helper function with within elephant. Hence, select is a helper function select is a helper function within elephant here, right? So select can reference name, age, and can fly again at the top. Therefore, we can simply return name, age, and can fly since these variables or attributes are already passed into this outside function, and that's the whole thing. This is a bit of a weird problem, but it's kind of a build-up for understanding how helper functions might go into classes in the future. In the future, you'll see some structure in green, all right? Something like class elephant, I can't spell. And then this will have something like name, age, and whatever else we want. And I'm writing this in Java syntax because that's what CS61B will teach you, the sequel to this class. And then we can write functions like public static, followed by whatever else. And then this function will do something here. So this is just a little sneak peek into this structure of classes and object-oriented programming seen in Java and other languages. And that's what this question specifically is trying to emulate. If you don't understand this question and don't understand why this is even useful at all, don't worry about it. We'll cover it more as we get to object-oriented programming later on in the class. Anyway, I hope this video was helpful, that it's a good walkthrough at the end of the week. Please let me know if you have any comments or suggestions. For those of you who are my normal subscribers, sorry if this is a little bit out of the normal, but I hope it was still helpful in learning tree recursion and data abstraction in an applied kind of handwritten way. And for those of you who are my students, thanks for watching this. I'll see you next week. Bye.